Hi, in this video I want to talk shortly about the topic of d-seperation. A Bayesian graph tells us how different variables relate to one another. The joint distribution P, A, B and C, or let's take D, we can rewrite that as P D given A, B, P from B given A, and P from A. And now this graph tells us that we can cancel out A here because D only depends on B. So now we want to ask this graph some questions and he can answer it for us. Given D are C and F independent or not, and or same given B and G or is F and C independent. Just some examples. Now this is what we call d-seperation, and it can easily be answered with three basic rules. This algorithm was invented from Jordan in 2007, and I have it out of the book from Murphy. So rule number one is if we have some chain of random variables in the graph with A, B and C, and what we want to know is given B are A and C independent. So given B are A and C independent. And it's pretty simple with this theory. Given B, it's as follows. We want to throw a ball from A to C. And if we can throw it easily through, we know that A and C are not independent, but if we're blocked somehow, then we know that A and C are independent. And now if we not observe B, we can easily throw a ball through here to C. But if we observe B, we imagine here some walls and the ball will fly here, but it will bounce back. Exactly the same if we want to throw it from C to A, it flies to the wall and bounce back. Rule number two is one node and two outputs, and we have A, B, C, and we ask again the same question. Node A and C independent given B, and we imagine again the ball. With nothing observed, we can easily throw it to here, but if we have some observation of B, we imagine again some walls here, and if we want to throw the ball, it just bounces back. Now rule number three is I call it all-in-one rule. We have two nodes here and one node here, and all nodes flow to one node. And now if we want to throw a ball here from A to B over C, we throw it to C, but it just falls down. So A and B are conditionally independent given C, but if we observe C, we imagine again here some wall, and it does not bounce back to A, but it bounces back to B, and B bounces back to A. Special at this rule is if we have some more nodes down here, we can have arbitrarily much, and we observe here again here this one, let's call it, we observe D and have here C and A and B, and now the question is A and B independent given D, and this is exactly the same. We imagine here some wall and it bounces back here to B. And with this new gained knowledge we can make some examples. Some simple examples. Let's take something like that. And now let's ask A independent of B given E. And that what was the last one, what I asked before, and we can ask it rather simply. The ball, we imagine this one is observed, yeah, imagine a wall here, ball flies back up to B. Okay, let's make something more difficult. Depend of E given A and B. Let's mark the ones we observed, that's A and B, and we are here at D or E, and we throw the ball straight to E, so we can answer this with no, it's not independent, right? Let's make a last one. Now the question is B given, or B independent of C given A, and let's mark the one we observe. We observe A, and we are here at B, and we want to throw it up here, but we know, oh, here's the wall, so it bounces back. We look if we have another path, we go here, but we know, okay, the ball just falls down here. So we have no way from B to C, and we know, okay, they're independent, condition independent, yes.